In this tutorial, we will show you how to perform iterative simulations using equidistant displacements. Using a 4F telescope with a focal length of 10 millimeters, we will move the inspection plane around the focal position. In this case, that position is 40 millimeters in the Z direction. The objective is to analyze the beam size as a function of the inspection plane's position. The video description includes a link explaining the step-by-step process for simulating a 4F telescope. For iterative simulations, you need one component to perform the simulations within the desired range and another component to record the simulation results. Add the component that initializes the data frame. To do this, select Data Frame, and from the list of elements, choose the Simple Table component. Reopen the component menu, and within the iterative category, select Linear Spaced. By clicking on the Linear Spaced node, we configure the initial and final values, as well as the number of points for the iterative simulation. Note that the block has a blue output node called Value. This node will have different values during the iterative simulation. There will be 30 points starting at micrometers and ending at 20 micrometers. Since we want to move the inspection plane in the Z direction, we must click on the inspection plane node and make the delta pose Z numerical property public. This is done by tapping the share icon in the desired field. We choose to modify the delta pose Z property because it allows us to decouple the manual configuration from the disturbances we wish to simulate. We connect the value output of the linear spaced node to the delta pose Z input with a wire. This tells the simulator that we want to perform an iterative simulation by modifying the delta pose Z parameter. However, in addition to the iterative simulation, the simulation must be recorded and visualized. The 3D viewer only shows the last point of the iterative simulation. To record and visualize the other simulated points, data frame components must be added for that purpose. We add the add number block, which allows us to record a numerical value in the table. To connect the block, you must specify the table to which you want to add the value and the value to be recorded. In addition to recording the Z-axis disturbance value, we want to record the output field of the inspection plane. To do this, add the Add Beam Field component. As with the previous block, you must link the table to which the field data will be added and the field to be recorded. When you click Add Number, you must specify the name of the data frame column. In this case, I'll name it Delta Z. For Add Beam Field, it already has a predefined name that we can leave as is. It is important that the data frame column names are unique. If you want to evaluate the field or a number in multiple locations, always ensure they have different names. The following components to be added are all found within the data frame category. They will allow us to visualize the beam size on the inspection plane. Add the End Load component, which tells the simulator that all columns have been added. This component must be linked to the last element that adds columns. In this case, it is Add Beam Field. Next, add the Represent Headers component, which lists all the columns of the data frame. The column names will be useful for creating the figures. Add the Represent in Plot component, which allows us to plot a series by selecting two columns from a data frame. Both Represent Headers and Represent in Plot can only be connected to the output of an End Load component. Note that the Represent Headers and Represent in Plot tabs have been added. We run the first simulation, which will allow us to determine the names of the data frame columns. Clicking on the Represent Headers tab displays a list of all variable names along with their descriptions. As you can see, the first variable in the data frame is named delta Z, along with its data type. The remaining variables are associated with information from the beam at the inspection plane position. We can see that no information has been loaded into the plot yet. This is because we haven't associated the data frame column names with the series values. To do this, click the Represent in Plot node and fill in the properties. For the X series name property, enter delta Z. And for the Y series name property, enter the name that refers to the beam size on the inspection plane. Then we assign names to the axes along with their units. Clicking the Simulate button again runs a new simulation and plots the beam size on the inspection plane. Note that the minimum coincides with the 0 position and is 2 micrometers, consistent with the 4F configuration. You can double-click on the Plot tab and rename it. In future videos, we will explore other aspects of iterative simulations, such as Monte Carlo simulations, mechanical stability studies, or sensitivity analyses. In other videos, I will explain how to perform simulations using diffraction and interference phenomena. Thank you very much for your attention. I hope you found this tutorial useful. If you have any questions, please leave them in the comments section. See you in the next video.